Good morning everyone. In today's video lecture, we'll learn about aquametry under the course of pharmaceutical analysis. So we'll check the different methods for water determination using different aquametric methods like Karl Fischer Titration or azeotropic method or different thermogravimetric analysis. So let's start. So what is aquametry? Aquametry can be defined as the quantitative determination of water present in any sample or products. So methods include Karl Fischer titration, reaction with acid chloride and anhydride, oven drying, distillation, and chromatography. So samples can contain water as solvent, as an absorbed water, as water of distillation. Actually, aqua means water and metry means measurement. So by aquametric method, we usually measure the quantity of water in any pharmaceutical sample or any other products. So let's discuss the importance of moisture determination. So when dealing with expensive material, even with large quantities of less costly materials, water can be considered an adulterant. Physical properties of a material are modified by its water content. Physical stability of the product may be hampered in the presence of water. Many pharmaceutical procedures such as granulation, tablet formulation, coating operation are also affected by water content. Major problems in manufacturing includes capping, peaking, sticking may arise due to moisture content. So these are the rationale for water determination because water may cause different problems in pharmaceutical products, including solid dosage form or liquid dosage form. So the determination of moisture content is very crucial during can be in tablet formulation or capsule formulation or liquid dosage form formulation or any other things. Moreover, small amount of moisture can also cause the development of microorganisms in any preparation. Moreover, many products are hydrolyzed in presence of moisture. Microbial growth is also potentiated by the presence of moisture. Then many chemical reactions involve water either as reactant or product. Such process can be followed or a reactant can be acid by quantitative determination of water. Okay, so we can also see that the drugs or molecule which are having some ester group or amide group can degrade easily upon the presence of water because uh, how these bonds are formed, this bond actually formed by the removal of water, and hence if you have some water in your preparation, then obviously this amide bond or ester bond or acid anhydride bond will easily uh, may break down in presence of this uh, water or moisture. So we'll see different ways or of determination of moisture content. We can determine moisture content of a sample by various methods, which can be categorized into two groups. One is physical method, another is chemical method. So in physical method, usually no chemical reactions are performed. Okay, usually this is some physical methods like use of drying oven or analytical balance, then thermogravimetric analysis or TGA, differential thermal analysis or DTA, then azeotropic distillation. Other physical methods are spectroscopic method, gas chromatographic method, electrochemical method, conductivity dielectric method, coulometric method, etc. So we can see here these are physical methods because usually no reaction is taking place here. Okay, we can say you are just applying your sample and you are just getting your result. This is the physical method. But in case of chemical method, we will say that several reactions are taking place and we are determining the moisture content by utilizing different reagents or chemicals, etc. So chemical methods include trimethic method or Karl Fischer procedure. This is the most commonly used method for water determination. It is actually performed in our pharmaceutical industries. Okay. Then other chemical procedure include inorganic reagent, organic reagent, and colorimetric method. So let's discuss the physical method for determination of water. So gravimetric method So gravimetric method can be of two types, like thermal method. This technique is based on loss on drying upon loss on weight upon drying. Then procedure is just you keep the sample, then give it heat, then loss of weight, and loss weight is the amount of moisture. Simple method that we have already done in our laboratory. However, you can also perform water determination by using absorbent. In this method, water absorbent are used to absorb moisture presence in the sample. Then the gain weight of the absorbent is determined, which is actually the amount of moisture of the sample. Absorbent that have been classically used for this purpose include anhydrous magnesium perchlorate, then calcium chloride, calcium sulfate mixture, etc. Now we'll see thermogravimetric analysis. It is suitable for material not sensitive to heating, that is thermostable material. This technique offers a more sophisticated approach to study loss in weight. This method involved the continuous weighing of the sample as it is heated at a constantly increasing rate. The resultant curve of the change in the weight versus temperature may have analytical chemical applications that include the determination of moisture. Usually, we keep the sample in this machine, then the temperature is increased, okay, in a constantly increasing rate. For example, 5 degrees Celsius per minute, okay, or 10 degrees Celsius per minute. Okay, this temperature is increased time by time. And for example, 25 degrees Celsius, after that it will become 35 degrees Celsius, after some time it will become 50 degrees Celsius, and this will be going on up to like 300 degrees Celsius or 400 degrees Celsius. And whenever this is happening, the obviously the moisture that is enclosed in the sample will evaporate. Okay, those drugs which contain no constituent volatile at 15 degrees Celsius other than water, specific quantity of drug is accurately weighed and then dried in oven at specific temperature and the time until the desired moisture content is reached. So that is how we usually measure the loss on drying or presence of moisture content. You can see here there is a graph. For example, this is the x-axis is showing the temperature, which is increasing time by time, and the y-axis it shows the drugs amount in percentage. Okay, you can see first of all there is 100% drug, no problem. So you're increasing the temperature, it's 100 degree, 200 degree, you're just increasing it, okay, no change. But whenever it is around 350 degrees Celsius, then you can see there is a sharp decline of the uh, axis, okay, sharp decline of the graph, you can see here. So what this actually means, this means your water content has evaporated at this temperature. Okay. So it also mean that your product may get degraded at this moment. Okay, as it is thermogravimetric analysis, actually this means it means the removal of different volatile content or any other water from this. Okay, so you can easily determine the purity of this compound, because after some time if you have a graph, okay, this is your experimental graph, but in another lab you have found out, or in another day you have found out a graph like that, then what will it mean? Mean there may have some variability of the temperature. It may be due to the impurities or due to the chemical degradation. This change may happen. Okay, so actually by studying the graph with the literature, we can easily understand what is the purity of our compound, or what is the nature of our compound, or what is the moisture content of our compound. Okay, your graph may be like that, okay, also may be like that, then it means that you may have some other impurities, or you may have degradation of your compounds, whatever it can be. But always it gives us idea about the amount of volatile content or the purity of the compound. Okay, for example, you are claiming that yes your API is not containing so much moisture, but whenever you are just analyzing your sample, you are finding that just your water has increased a lot, or your moisture content seems to be very high. Obviously it will may affect your degradation of the product or tableting problem. Okay, it may create a lot of problem. So this is the overall idea that we may get from this thermogravimetric analysis. Okay, this has already be done in our lab. It shows the percent of moisture content. It is very easy because in the initial weight minus the weight of the sample after heating, and the difference is divided by initial weight. So most vegetable drugs contain various amount of volatile substance such as essential oil, ether, ester, amines, and the drug contains matter other than water which is volatile at 150 degrees Celsius, then weight of the volatile substance is determined. Soluble extractive shall be determined and the weight is subtracted from the weight loss by the drug upon drying. The difference to be taken as the moisture content of the drug. Okay, however, there are a lot of disadvantages, like this procedure is not free from error as it is a physical method. Yes, obviously there may have some anomalies. Then water is slightly miscible with ether. Some of the moisture content uh, may be extracted by anhydrous ether and determined as volatile ether. Okay, actually, ether is used in this case, and obviously water is slightly miscible with ether, and there may have some anomaly in the result. So this is a problem. However, you can also determine your moisture content without heat. Okay, by this physical method, like moisture can also be determined in absence of heat. Drying is accomplished at reduced pressure, and absorbent is used to absorb water from the sample. For example, calcium sulfate, calcium chloride, silica, anhydrous magnesium chloride, barium oxide, etc. are used. An inert gas is allowed to carry the water lost from the known quantity of sample to the absorbent, which gain in weight is then determined. Now, we will say another physical method, that is azeotropic method. So in this method, water immiscible solvent like benzene, toluene, or xylene is added to the material containing the moisture and then co-distill any water present. Okay, it utilizes a machine as like a Soxhlet extractor, in which first of all sample is mixed up with toluene or benzene or any other solvent. Okay, this solvent need to be heavier than water. I will say the reason behind this later. Just first of all, sample is mixed with benzene or toluene. Then, if our sample has any water content, then upon the addition of heat, this water will evaporate. But the boiling point of benzene, toluene, or xylene should be higher. Okay, the solvent that we are utilizing, its boiling point should be higher than water. Why? Because it will otherwise it will evaporate it. We actually need water to be evaporated. Okay, then recondensation of the vapor, this vapor means water vapor, results in the separation of the water from the immiscible solvent, making it available for the volumetric measurement. It is also known as co-distillation method. So why co-distillation? Because co means whenever you are just utilizing some other solvents concurrently. Okay, like water and benzene is concurrently used, and that is why it is called co-distillation method. This method is specific for the determination of water content more than 2%. Okay, whenever your sample is having some uh, more water, okay, it's containing more water than more than 2%, then you can use this azeotropic method. Okay, then question may arise, then if we our sample contain water less than 2%, then which method we should use? Obviously that should be Karl Fischer titration. The solvent with a specific gravity less than 1 have added advantage of allowing the water to form a layer at the bottom of the trap which can be measured directly. So you can see here there is a graduated tube, and uh, this is the condenser, and here there is a round bottom flux where we keep our sample and the toluene. So whenever we are heating this, then the moisture present in the sample will go up because it is in its boiling point. But the boiling point is toluene is much more higher than to the water, so moisture will go here. Okay, then when moisture will come here, then it will condense. Okay, whenever it will get condensed, obviously it will get converted into liquid. Then this liquid will come here drop by drop. Okay, and this is your graduated tube. It measures the amount of liquid which has come here, and this liquid is nothing but water or moisture. That is how we usually determine the amount of moisture. And your excess gas, or that mean the solvent will get out from this direction. This is the condenser. So this is the overall method, and this uh, is called Dean and Stark moisture determination. So it shows the overall procedure. A known weight of sample is placed in a flask with an organic solvent such as xylene or toluene. The flask containing the sample and the organic solvent is attached to a condenser, and the mixture is heated. The organic solvent must be insoluble in water, have a higher boiling point than water, and be less dense than water, and be safe to use. This is all about the nature of the toluene or xylene that you are using. The water in the sample evaporates and moves up to the condenser, where it is cooled and converted back to the liquid water, uh, which can trickles into the graduated tube. When no more water is collected in the graduated tube, distillation is stopped and the volume of the water is retrieved from the tube. So this is the overall method that I have described earlier. So you can see the overall pictures, overall procedure. Here we keep our sample along with toluene. Whenever we are giving heat, then yes, if your sample contains water, then this water will get evaporated, and whenever it will get evaporated, it will come into the condenser. So in this condenser, water, the moisture will be condensed into water, and the uh, water will come here drop by drop, and this measures your water content. So here no chemical reaction of the water has taken place. So it is a physical method. So you can see here heat is applied. There is the thermometer. You can see for example. So water cooling. This is the condenser, and this is the funnel. This is water in distilled. Okay, you can see the amount of water that has been distilled here. Now, there are some applications of azeotropic method. Azeotropic distillation have extensive application in the determination of moisture because of the simplicity, economy, efficiency, and accuracy. The method is especially useful for the moisture determination in bulk materials such as plant part and for medicinal soap solution. There are some advantages like recovery of solvent is possible, then useful for moisture determination in bulk materials such as plant part and for aqueous solutions such as medicinal soap solutions. However, there are some disadvantages like it's not applicable for heat sensitive materials and not applicable for some small amount of samples. Okay, so these are the some pros and cons of azeotropic method. Now we will see the most commonly used method for water determination in our pharmaceutical area, because azeotropic distillation is some has some limitations because it's very much physical, and the uh, machineries or equipments that is required for this water determination by azeotropic method is much more complex and seems to be very sophisticated. But the Karl Fischer titrator is just a single machine. Okay, it's a small machine. It's like some small centrifugation machine. The size is like that, and it's not so much complex as that of azeotropic method, because the azeotropic method required some round bottom flask, a condenser, then a graduating tube, a lot of things. Moreover, solvents required, very critical things. Okay, so that is why Karl Fischer titration has gained much attention for the analyst and chemist. So in 1935, German chemist Karl Fischer described a specific trimetric method for the determination of water remains the most generally applicable procedure, as it is trimetric method, so there are some reactions. Karl Fischer titration is widely used analytical method for quantifying water content in a variety of products. The fundamental principle behind it is based on the Bunsen reaction between the iodine and sulfur dioxide in an aqueous medium. The overall reaction takes place in the presence of methanol and a base, that is imidazole or pyridine, in the following manner: that iodine, sulfur dioxide, then 3 mole of base, then methanol, and if you this is your sample that contains the water. Okay, it will react with iodine, and this product will be formed. It clearly shows that 1:1 ratio of H2O and iodine is the basic uh, principle for the titration. Okay. So this is the overall update, that 1:1 ratio. This ratio is important. So let's discuss the determination of water in sample procedure. So it can be done by direct titration and back titration, where excess reagent is added and excess is back titrated with standard water in methanol solution. So let's discuss the basic principle. Water and iodine are consumed in 1:1 ratio in the above reaction. Once all of the water present is consumed, the presence of excess iodine is detected volumetrically by the titrator's indicator electrode that signals the end point of the titration. The amount of the water present in the sample is calculated based on the iodine concentration in the Karl Fischer titration reagent. Okay, and the amount of the Karl Fischer reagent consumed in the titration. So a question may arise that what are the rationale of using sulfur dioxide, iodine, pyridine, methanol, imidazole? Okay, what are the rationale of this, or what should be the constituent or the amount? Okay, it shows the overall volume of the of your reagents. All the components must be free from water. 1 ml of Karl Fischer reagent, when freshly prepared, will react with about 5 milligram of water. So the molar ratio is 1:3:10. So when prepared, it is generally practiced to increase the stability of the reagent by adding sulfur dioxide to a stock solution of the other components the day before actual use. Numerous side reactions may occur among the constituent substances. Freshly prepared reagents therefore has a strength about 80% of the theoretical value, but this rapidly falls to about 50% in 1 month and 40% in 3 months. Okay, so classical KFR contain pyridine, innoxious carcinogen. Okay, so that is why today pyridine-free uh, reagents like imidazole, okay, are used. These pyridine-free reagents are available commercially for volumetric and colorimetric Karl Fischer procedures. Modern Karl Fischer reagents use imidazole or other amines as the base instead of pyridine and are supplied as either one component reagent, like which contains all necessary components in a single solution, usually in methanol or any other alcohol, and two components reagent comprises a solvent and a titrant. This system offers superior stability. So reagent type is volumetric. Components are titrant and solvent. So titrant is iodine in methanol or ethanol, then sulfur dioxide, imidazole, methanol, ethanol. Okay, so essential component of KFR. Why iodine is used? Iodine reacts with water in 1:1 ratio. Then sulfur dioxide, it is reducing agent. Okay, then the base, it neutralizes the acid, because where acid comes from? Acid usually comes from the sulfur dioxide, because uh, the water and sulfur dioxide will react with each other to produce H2SO4, sulfuric acid. Okay, so overall our solution would be acidic. So to neutralize the acid, we use base. Okay, for example, imidazole. Okay, nitrogen containing base. Then alcohol, it forms stable ester, that is an essential reactant. We'll see later that how it forms the ester, because there must have some stability of your product. Okay, of your product that has been formed by this reaction, and the stability has increased if stable ester bond is formed, and this bond is formed by using alcohol. The overall reaction during KFT consumes water, iodine, sulfur dioxide, and alcohol, typically methanol, in the presence of an organic base like imidazole. The key points are Iodine and sulfur dioxide react with water in a 1:1:1 stoichiometric ratio, and alcohol is required to form stable alkyl sulfide star, driving the reaction to completion. A base is necessary to neutralize the acid produced. So standardization of KFR. KFR must be standardized strictly before use as a result of stability problem due to the side reactions. Titration against standard water in methanol solution, then titration against the weight quantities of hydrated salt like sodium tartrate dehydrate, it will be dihydrate. Okay. Then procedure for standardization, about 35 to 40 ml of methanol is placed in the titration vessel and added sufficient amount of the KFR from burette to give the characteristic endpoint by characteristic amber color, and quickly 100 to 150 milligram of sodium tartrate is added. As the titration proceeds, a canary yellow color appears. Okay, so this is the overall procedure for standardization, because before using any other reagent in our analysis lab, we obviously need to standardize it for further use. Okay, so this is the overall procedure for standardization. So put the selected solvent in the titration container, titrate the solvent until it becomes anhydrous, then add the sample to the container and titrate the water content corresponding to the new reagent. So we will use this standard equivalent value later when we will do some practice problems. Okay, it shows the overall pictures of your machine. It's not um, too big. Okay, it's too small actually. You can see the reagent bottles, the waste, the solvents, okay, the reagents, the kefir. Okay, here actually overall reaction takes place here. We need to put our sample, the powder or granules, in that location. Okay, then the reaction takes place here, and it will ultimately generate some chemicals. Okay, generate some products from the reaction, and ultimately our water content will be determined by 1:1 ratio. Okay, the more iodine you record, the more water content our sample will have. And we also perform a titration by determining the endpoint. Okay, we'll see this in the upcoming slides. So what is the overall chemistry of this reaction? Okay, we have already known that usually iodine is used, sulfur dioxide is used, alcohol is used, methanol is used, then nitrogen base, that is pyridine or any other imidazole is used. Actually, how they react with each other to give us the ultimate product or to give us the overall determination of the moisture content. In the presence of water, iodine will be reduced and sulfur dioxide oxidized in the following manner. So it shows the reaction. The reversibility of the reaction can be prevented by using a large quantity of pyridine. The concentration of the pyridine is sufficiently large so that iodine and sulfur dioxide are complexed with pyridine as like that. Actually why pyridine is used? Pyridine is used for um, decreasing the reversibility. You can say this is a reversible reaction. Okay, and if you use pyridine, then it will be a irreversible reaction. Okay, there will be a tick sign here. The pyridine sulfur trioxide compound, an inert salt, reacts in turn with the methanol present to form the pyridine salt of methyl sulfate. Okay, so why methanol is used? Methanol is used for stabilization of the product. you know uh, then this salt will further react with this methanol and stable product will form. Then question arises, if it is not formed, then what is the problem of actually if it is not formed, this may further react with that to give rise to this reactant. Okay, and our overall purpose of using this methanol will get destroyed or diminished, whatever it is. So actually to make it stable, we usually perform this. Thus methanol prevents the further reaction of this with water. Okay, it has formed in stable compound complex. The last reaction is undesirable because it is not specific to water. It can be prevented by using excess amount of methanol. Okay, if you don't use methanol, then this will react with water to form this compound. Okay, which is very unexpected. as it is not specific to water, because water should react with iodine, water should not react with this. Okay, if you don't use methanol, then your water will react with this, then it will create some undesirable products and you will have some anomaly in your result. Okay, so after performing our titration, we have to interpret our result. So there are two types of titration, or in two ways we can interpret our result, that volumetric KFT and another is coulometric KFT. So as the name suggests, volumetric means you will do some titration, volumetric titration here. Then coulometric by coulometry you will see the electrical change. Okay, the electricity change or the some electron sharing in coulometric method, and your overall water content or moisture content can be determined by coulometric method. So in volumetric method, iodine is added mechanically to a solvent containing the sample by the titrators budded during the titration. It detects the endpoint of the titration using the double platinum pin indicator electrode. Water is quantified based on the volume of the Karl Fischer reagent consumed. You can see this is an usual method. Okay, we have already said that uh, our 1 mole of water will react with 1 mole of iodine. So this is the basic principle for this volumetric KFT. Volumetry is best suited for determination of water content in the range of 100 ppm to 100%. Okay, so it's for very large volume of water. But question may arise, then if you have small quantity of water, then which method should be used? Actually, for small quantity of water, coulometric KFT is used. So we'll see this now. Look at this line. Coulometry is best suited for the determination of water content in the range of 1 ppm to 5%. In the coulometric KFT, the iodine is generated electrochemically in the titration cell by oxidizing iodine from the electrolyte solution. The amount of electricity in coulomb required to generate the iodine that reacts with the water is measured. So in cathode, you can see this reaction took place. In anode, this reaction took place. Water is quantified based on the total charge passed as measured by the current in time according to the following relationship. Okay. Now, our analysis has been performed. Now it's the time for determining the endpoint, which will ultimately detect our presence of moisture. So usually endpoint is determined by other methods. Okay, in our lab we usually perform or usually analyze or test our see our endpoint by different visible methods like change in color. Okay, but however there is some photometric and amperometric method. So visible method, the color change accompanying the KFR is suitable for the detection of the endpoint in mini titrations. But some samples are colored. In that case, automatic titrations are employed. Then photometric method. In this case, absorbance of the titrating solution is measured as 5 to 5 nanometer. A plot of absorbance versus titrant volume is made. Before the endpoint, the absorbance remains close to 0, but after the endpoint, it increases linearly with the volume. The amperometric method. In this process, two platinum electrodes are polarized at a constant current. Before the endpoint, there is small residual potential established between the two electrodes, whereas in the endpoint, there is a large increase in potential with the introduction of the free iodine. So these are the methods for determining the endpoint. Now we will see effects of temperature, pH, or some other factors which affect the Karl Fischer reagent. Okay, first of all, we'll see the pH. Optimal pH range of the Karl Fischer reaction is from 5 to 7, and any acidic or basic sample need to be buffered to bring the overall pH into that range. Outside this range, following interference may occur. Low pH, if it is low pH and then it means it is strongly acidic, then the reaction is sluggish and may not go to the completion as the base is protonated. You know, our nitrogen base is used. Okay, so if our solution or the media is strongly acidic, then obviously our base would be protonated, because it will receive water, it will receive proton from any other acidic solution. And if our base is protonated, then it will not go for any reaction, because we have used our base for uh, formation of complex or for undergoing the reaction smoothly. Then another condition may arise. In strongly basic conditions, serious side reaction may occur. You know, if our reagent is very basic, then iodine disprotonation, disproportionation may happen, then star saponification may happen, then it can result in high erroneous value and fading endpoints. Okay, the sample with extreme pH must be buffered into the optimal range before titration. So let's discuss the advantages of KFT over other methods. Azeotropic method can be effective in case of high moisture containing substance, but KFT can detect trace amount of moisture. Heat is applied in case of azeotropic method, so heat sensitive products cannot be analyzed, but in KFT method, no heat is applied, so the heat sensitive material can also be used. In case of gravimetric method, volatile substance can cause error in the result, but in KFT method, there is no such kind of problems. KFT method is accurate than any other method. Only 0.1 to 0.1 0.1 to 0.2% error may occur. The endpoint of KFT can be detected visually, photometrically, or electrometrically. Water can be detected from most classes of organic sample. Okay. However, there are some limitations of KFT method. The method is only applicable for those substances which neither react with any components of the reagent nor the hydrogen iodide, which is formed during the reaction with the water. Okay, ascorbic acid will be oxidized by the iodine present in the reagent. Carbonyl compound react with methanol forming acetal or ketal. Oxidizing agent, for instance, chromate, peroxide salts or hydroxides. Then reducing agents such as tin salts or sulfides. Okay, compounds that have a tendency to form water with the ingredients of KFR, for instance, basic oxide salts or carbonic acid. Okay, so these are the overall limitations for KFT. Now, this is our final segment. In this segment, we will do some uh, practice of problems like determination of water. Okay, so we have already informed that we require some volume of KFR for some weight of sample. Okay. For example, I have given you 5 gram of sample, and I'm telling you that yes, please determine the moisture content of this 5 gram of sample. This is our actual analysis that we should do. Okay, I'm giving you the sample, and you have to just calculate the amount of moisture. So then how will you calculate? Well, just measure the volume of KFR required, nothing else. That means I have given you 5 gram of sample, that would be the 5000 milligram. Then your volume, you will determine this by the KF reaction. Okay, that around, for example, 10 ml, you have found out 10 ml. So V means 10 ml of KFR is required for our 5 gram of sample. Okay, then W gram of sample contain F into V. What is F? F is usually standard value. Okay, it would be given in your question, no problem, don't worry. And the procedure for determining the F has been shown here because it is the equivalent factor. Okay, it would be given in your question, so you don't need to worry. So how it is determined? Actually, equivalent factor is determined for our sample, our KFR itself contains some water, and you have to minimize this. Okay, that is why we perform this equivalent factor. Okay, so it is determined by that one. Just to go through this. Okay, then 100 mg contains how much? We will determine this. That means we will have some FB divided by W into 100%. This is your moisture content. So F means your F value, that is the equivalent factor. It would be given like 0.15, 0.25. Okay, then V is the volume that you have found in your lab, and weight that I have given to you. Just three values, nothing else. Okay, for example, I will show you math in upcoming slides. Calculate the percentage of the moisture of aminosalicylic acid if 9 ml of KFR. So 9 ml means 9 ml V. This is the V. Okay. Now water, equivalence factor of 4.1. you can see the unit of equivalence factor is milligram water per ml. Just always remember this, the unit milligram water per ml is consumed by 5 gram 5 gram 1 gram sample. 5 gram 0.1 gram means 5100 milligram. So you have found out the W, this is the W, this is the V, and this is the F. I think you can now easily determine the water content, because we know water content is FB into W divided by FB by W into 100. Okay, just put the values and you got the results. You can see the water content is around 0.7%. Usually your value will come 1%, 2%, 0.5% like that. If in any answer you have the water content like 90% water, that means it's impossible. You have water content 120%, that is impossible. Okay, just uh, see the usual value of these maths. Now I think you can perform all other maths. Just keep in mind that this is the equivalence factor, which unit is milligram water per ml. Just keep it in your mind. And obviously, just keep also this in your mind that you have to convert all of the unit into milligram. So this is the overall calculations. So I have given you some other practice problems here. Just perform this yourself. You can easily do this. So this is the overall lecture from Aquametry. If you have any confusion, please inform me in the comment section. Thank you.